Hello, everyone. Welcome to the Physics 123 Section 1 review session. Today we will be going over some potential questions for this week's quiz. Okay, so let's say we have a surface, right? And we have a block. Now, this block has a mass m, right? And I push it with a force F across the table for a distance of d meters. Okay? Now, there is also in this block, there is a force friction right here. Force friction, right? There's also on this block another force of mg, force due to gravity, and there's an equal and opposite force normal. Okay, now this force friction is equal to mu k times the normal force. Okay? Now, let's say I wanted to find the work done by an external force. Right? That would be this force F here. Okay? Hold on, just 1 second, please. Gotta calibrate my smart board. Okay. All right. So the work done, right? Work due to an external force is equal to integral of F dx. Okay? All right, so we have our force F here. That's what we're talking about. Now this force, we're going to say it's a constant force. Let's say F is equal to 30 newtons. Okay? Now, since it's a constant, we can pull it out of the integral. We can say work is equal to F from 0 to 3 dx, which is just equal to F times 3 minus 0, right? Now, I said 3 because this is 3, okay? Okay. All right, now that's how we do it. So this happens to be 90 Newton meters, right? Because this is in meters, this is in newtons, which is equal to 90 joules. Okay? Now, we also have, let's say this question asks us, what is the energy, the change in energy due to friction? Okay? So, here's a fun fact. Delta energy equals work due to friction. So this is friction, this is friction. Okay? Now we know the work due to friction is equal to the integral of force friction times dx from 0 to d. Now we can just say this is also equal to a constant force. Well, first let's define force normal. All right, the only forces acting in the x or in the y direction is the force due to gravity and the normal force. Okay, so they must be equal and opposite. Therefore, force normal is equal to mg. Right? You know the force friction is mu k times n, so it really is mu k times mg, which is a constant, so we can pull it out of the integral and say mg mu k times the integral from 0 to d, sorry about that, 0 to d dx, which is equal to m times g times mu k times d minus 0. Okay? Now I did not give a value of m in this problem or mu k, so we can just leave our answer in this form. And this is also equal to m g mu k d, and this unit is in joules. I used green because we're using units instead of variables now. Okay? Now, we can use the work energy principle to find the total kinetic energy of the block in its final position. Okay? All right. So we can say there is no change in potential energy equals delta KE plus delta PE, but this goes to 0, right? Change in kinetic energy starts out at rest, but we can just write the general equation, 1/2 m v final squared minus v initial squared. All right. Initial velocity is 0. All right, and this is also equal to the total work done. Sorry, I meant to use a summation symbol. To the sum of the work done. So the work due to friction is negative because it acts in the opposite direction of motion. So this is equal to the work due to the external force, which is F times 3F minus mg mu k times d. All right. Now, if we wanted to find the final speed, or velocity of the block, we would remember that we can just take the square root. So V final, let me use a different color. Use red. V final is equal to the square root. We bring this over. It's 1/2. Bring over the m. M cancels. Right? Actually, it doesn't. So we can say 2 times 3f minus mg mu k, and all of this is under the square root, by the way. Mu k times d, that's all multiplied by 2 divided by m. Okay? Whatever that number is your final velocity. Does anyone have any questions? Oh, no one's listening. Cool. That's always a good sign. Well, let's see if there's anything else we could go over. Let's work out chapter 7, example 6. I don't have your textbook. Let's just do an example. Stand by. Okay. Let's do an example. Let's say I have a ceiling with a spring that is compressed. There's a mass here. So, spring has a normal mass, so here's x, here's x naught. X naught is equal to equilibrium. Okay? Now, I want to find the velocity at equilibrium. So it starts out at rest, so v naught equals 0. I want to find v of x. This is v of x naught, right? Okay? Now, we can say, let's change the constants. Actually, let's just use variables for now. Okay, so I want to find the velocity when m is here. So I will use my work energy. Remember that change in kinetic energy equals work. So not the integral of work, just normal work. Okay, so this starts out at rest, which is 1/2 mv of x naught equals the work done. So remember that work done to a spring, say, movement goes from, let's, okay. The work due to a spring is, or the force to a spring is kx dx. We also have the work due to gravity plus force due to gravity is mg from, you can just say height x naught. Now the reason I use this is because that's when spring is not extended. So it goes from, I accidentally switched limits, it should be down here, but I added a negative sign there, so it cancels. Okay, so that ends up being equal to 1/2 k delta x squared. Why does it keep doing that? Good question. Half times k times delta x squared. Okay. And since we're doing delta x, which is positive, plus mg delta h. Okay. This is 1/2 mv squared. That's equal to that. So I want to find the final velocity, so I can say v equals the square root of 2 divided by m times 0.5, but it's factored. Oops. I really hate this smartboard. It's pretty irritating actually. Times 0.5 times k delta x squared plus mgh. There we go. This is our final answer. Does anyone have any questions? Oh, there's no one here. Never mind. Thank you for watching. I hope you enjoyed it. That's me.